So our last talk of the day and of the workshop is going to be on this is some miniKanren tooling, which I think is in great need. So I'm very interested to learn about how we can actually catch up with tooling and make the programming easier to understand, hopefully for both beginners and experienced miniKanren programmers. Yeah. Well, thank you.
Yeah, thank you so much. Do you want to share the slides, Daksh?
Yep.
Okay, so hi, I'm Sloan Chochinov,
And my name is Daksh Malhotra.
and this is joint work with Gregory Rosenblatt, Matthew Might, and Lisa Zhang. And today we're presenting our work on a miniKanren profiler. We want to show you how we can use this profiler to optimize miniKanren programs by making programs reduce their search space as soon as possible. In other words, fail fast.
In order to show you the profiler, we need to write a relation. And here's a relation we want to write, proofo. So proofo is a relational proof checker for purely implicational minimal logic. Proofo supports 3 proof types: use, which proves a proposition by using an assumption that was already made about that proposition being true; assume, which proves an implication by assuming the antecedent, then proving the consequent; modus ponens, which proves a proposition by proving an implication where that proposition is a consequent, then proving the antecedent. So proofo takes a proposition and a proof and succeeds if the proof is a valid proof for the proposition. We would have liked to implement this relation live, but we did come prepared with our own. So here is our implementation of proofo. You can see 3 condy branches corresponding to proof types we just talked about. The first branch deals with use. The second branch deals with assume. And the third branch deals with modus ponens. So we're going to try run some of these examples we have on the slides. And here's our profiler. So just to make sure our profiler works, we're going to run our 2 example queries. Here is one of our example queries, and we're going to do a run all statement. Or sorry, we should run for one solution. And as you can see on the right here, we have indeed one solution. And this solution does look valid, so our code appears to be working. So now that we know our code works, let's try and move on to another example query. So here's a query to try prove a proposition. Sloan and I had a debate on whether this proposition actually has a solution or not.
It doesn't.
So let's try use proofo to prove this proposition and settle our debate. This proposition states that if A and B imply C, then swapping A and B should also imply C. Let's cast miniKanren to give us a solution to the proposition. Wait, Oh no! When I click the Run button, the interface appears to not be changing. In fact, even if I waited 5 minutes, it will have not changed, because this query does not terminate within a reasonable length of time. Maybe there's a way for us to optimize this query using the profiler, so that we can prove Sloan wrong once and for all. Instead of letting miniKanren run until it finds a solution, let's have it run for 100,000 steps. In our implementation, a step is just a finite small amount of computation. So by setting a bound on the number of steps, we're limiting the amount of time miniKanren will run for before giving up. We just ran this again with 100,000 steps, and we can see that miniKanren is done running. We can see the profiler's report on the program point statistics on the left. The program points are these blue highlights on the left. At the top, we can see various metrics to view, namely encounters, failures, failure ratio, successes, and success ratio. Each metric is represented with highlighting on encountered program points, where the strength of the highlighting is proportional to the value of the metric. After looking at each metric, we might notice something strange. There are 2 recursive calls in the modus ponens branch of this condi goal, but the second one has a much higher failure rate. By our motto, fail fast, we want to have as many failures as possible, as soon as possible in the program, in order to reduce the search space miniKanren has to consider. But here, the recursive call with the higher failure ratio is being placed after the recursive call with the lower failure ratio. Let's try to swap the conjuncts and see if that improves the running time of this query. We're going to rerun the query. So just now, the profiler UI updated, and we can see it completed the query in 37 milliseconds. Also, viewing the solution panel on the right, we can see that we do indeed have a solution. So we were actually able to debug this program using the profiler. Well, what do you think about this proof, Sloan? Do you agree that the proposition is true?
Well, all right, I guess it's true.
I'm going to explain the other UI elements of the solution panel in a later example, like this and the path and stack. But first, I'll let Sloan talk about our implementation.
All right. So now I'm going to talk about how we actually get these statistics out of miniKanren. So to start, we added a couple new attributes to the state, path, and stack. The path is an ordered list of program points that have been evaluated on the state. You can think of it as sort of a record of which program points the state has passed through in order to get to its current constraints. And this is super useful to see which condi branches a state has been routed through, as we'll see in the next example. The stack of a state is much like the stack you would see in any procedural language. We push relation calls to the stack when they begin, and pop calls from the stack once all their subgoals have completed. We'll show why the stack is useful in a later example, but we also need it to track program point statistics. And speaking of which, on the next slide, I'll talk a little bit about how we track the statistics that you just saw in that example. So, of the 5 metrics we show for program points, we only really need to track 3 of them: encounters, successes, and failures. Success ratio and failure ratio can be calculated from raw failures and successes, so we don't need to explicitly track them. Tracking encounters is pretty straightforward. Whenever miniKanren evaluates a program point, we add 1 encounter. Successes and failures are a bit more complicated, since we need to consider whether the program point is a primitive goal, like equality and disequality, or a relation call like proof-o and appendo. So in the case of primitive goals, they always either succeed or fail right away, depending on the result of their evaluation. If a primitive goal returns a state, it succeeds, and otherwise it fails. In the case of relation calls, they always succeed in creating some subgoals, but the subgoals themselves may succeed or fail. So we only consider a relation call to succeed when all of its subgoals have succeeded, but if any one of the subgoals fails, we consider the relation call to have failed as well. This is a little bit different from how we treat primitive goals because we can't say right away whether a relation call is considered to succeed or fail. So now I'll pass it back over to Daksh for some more examples.
Next, we are going to demonstrate how solution paths generated by the profiler can be used for debugging. In this example, we'll be looking at an example that might be familiar to some of you, member-o, which determines whether or not an item is present in a list. Here is our attempt at an implementation of member-o. Member-o has two arguments, an item and a list, and succeeds if the item is present in the list. You can see that member-o has a base case and a recursive case, and which are used to compare each element of the list against X. Let's try out our implementation of member-o by running one example. In this query, we are asking to see what members, we're asking to see which, we're querying to see what is a member of this list. So after running the query, we can see on the solution panel to the right that we have 3 solutions, indicated by the range of indices 0 to 2. By typing each of these indices into the text field on the right, we can view each solution. So just to make sure that this relation is working correctly, let's try out another query. Query is similar to the last, except our list contains 4 copies. So our UI updated, but wait, hold on. There's 4 solutions? But there should only be 1. Something isn't right here. Let's take a look at each of the solutions to see if we can figure out why we are getting duplicates. Let's open up the first solution by typing the index 0 into the text field. Each solution in this panel is accompanied by its path and stack. Since these are solutions, the stack field will be empty, so let's only focus on paths. Our first solution has gone straight to the base case of member-o. Our second solution has gone through the recursive call once, then onto the base case. Our third solution here has gone through the recursive call twice, then onto the base case. And then our fourth solution has gone through the recursive call 3 times, and then onto the base case. Seeing this tells us that when we enter the recursive case of member-o, we want to be absolutely sure that we won't accept the same solution that we find in the base case again. Therefore, we want to add a constraint to the recursive case that's equivalent to the negation of the base case. The base case is just equal first x, so the negation would be not equal first x. Let's try add this to our implementation. So now let's try rerun our query again. We can see we only get one solution, as indicated by the 0 to the 0 shown in the solution panel. Thanks to the solution panel, we were able to successfully determine how to prevent duplicate solutions within a query. So, to show off one of our final features of the profiler, the ability to view rejected states, we want to introduce our last relation, selection sorto. Selection sorto is a relational sorting algorithm for piano numerals, where 0 is defined as the empty list and the successor for a number is the previous number with an S appended. Here's our implementation of selection sort. Let's try sort the list 2, 3, 1, and we expect to get back our sorted list 1, 2, 3. As you can see, miniKanren has found one solution, and we can see in the solution panel that it is what we expected. But since it's a miniKanren, we can try run the relation backwards as well in order to try generate permutations of a sorted list. So we're going to try query for all permutations. And the profiler interface hasn't refreshed yet again. Maybe this query doesn't terminate. Let's try restrict the amount of time by limiting the amount of steps. Also, it would be nice to view some states right at the moment before failure in order to get a sense for the search space miniKanren is considering. As it turns out, we can do that by setting the samples fields at the top of our interface to a non-zero value. Samples are a sampling of failed states encountered during a query, where a failed state is a snapshot of a state right before a primitive goal fails during execution. Let's try run this query for all solutions with 10 samples and limiting our steps to 1000. Now our profiler has updated, and as you can see by the solution, by the 0 to 4 in our solution panel, miniKanren has found 5 solutions of the 6 that we expected in 1000 steps. However, the 6th solution still was not found. Also, you can see the indices of failed states in the rejection panel here, similar to what we saw in the solution panel. Looking through some of the failed states, we can see that some of the lists miniKanren is trying to generate are way longer than our input list. We want to restrict this so that we can fail fast and reject these obviously incorrect solutions earlier. To fix this code, we need to write an additional relation. Here is same length, which succeeds when 2 input lists are equal in length. We can add a same length to selection sort early on in the evaluation order to try fail fast. So let's try this query again, unbounding the amount of time we can take. Now our query terminates, and we can see all 6 of our permutations in our solution panel. This means that we were able to use the rejection panel to profile a non-terminating miniKanren query.
So, what we showed you today were just toy examples, and the profile is very much still a prototype. There are some things that we don't support, but we think would be helpful for profiling and debugging miniKanren programs. And those things are, we don't support viewing the state at all points of execution, as opposed to viewing the state of solutions and failures only. We don't support profiling multiple queries as a test suite, and we don't reconstruct statistics of Conti and fresh blocks. We appreciate any feedback and discussion on what you would want to see in a miniKanren profiler. Also, you can find our GitHub repo at this link or by scanning this QR code. The repo includes a PDF of our paper and some of the examples we showed you today. And now we have some time for questions.